regions. This region will be talking about the dental clinical procedures. This region will be concentrating on the delivery and what is going to be delivered from the clinic to the dental lab. And the procedures that will be described here will be done by the dental technician. So this is the area of authorization for the dentist, and this is the area where the dental technician will be working. So if we begin at clinic number 1. The dentist has decided that this patient is suitable for a chrome cobalt RPD. Remind you that chrome cobalt is a definitive treatment, meaning that the patient should have finished all of the procedures before it, stabilizing his oral health, removing teeth that should be extracted, treating his periodontal diseases if he has any, and treating active dental caries. So chrome cobalt is a definitive procedure. So all of the dental procedures prior to that are not counted here. We are talking about clinic number 1 of the actual RPD procedure. So the patient is ready. We select our trays, and we then take impressions. We're going to take upper and lower impressions. These are usually done with a tray and alginate because this is a dentate patient. And this together, the upper and lower impressions, are delivered to the lab with instructions to pour them. So in the dental lab, the dental technician will receive this, disinfect it. If it was not disinfected in the clinic, then begin the pouring process. And I remind you that primary casts are poured using plaster. The pouring process will result in 2 casts, upper and lower primary casts. These primary casts will be also called study cast, because on them we study our design. Where am I going to place the teeth? Where am I going to place the components of the chrome cobalt that you have taken in your lectures? So I have to study this well. Studying it by vision will not be sufficient, because I could not see if there is an undercut and how much is it. I could not gauge it by vision. I need something more specific. For this purpose, I use what we call a dental surveyor. You will take the process of surveying in detail in the next demo. This instrument is used for recording and trying to analyze all of the components of RPD. Once we finish the surveying, we will have some lines drawn on the cast, mainly the survey line. We would have found undercuts suitable for our design. We complete the drawing trying to draw other components of the design until we reach to this design, which has all of the components drawn on the cast. As students, you should take an approval for this design from your supervisor. And the dental technician will also provide with this special trays to take impressions. These 2 go back to the clinic, casts with their special trays, and now we begin a process called tooth preparation. I would like to remind you that the natural tooth form is smooth and continuous, but it does not have places to place a specific guide plane or rests. So we do tooth preparation to make the shape of the tooth accommodate components as guide planes and rests. After tooth preparation are done and your supervisor approved these alterations of the teeth, a secondary impression is taken. I'd like to remind you that we remove the spacer before we taking the secondary impression. After we take the secondary impression, we have the final special tray with the impression material inside. We also do a bite registration procedure. And all of these are sent back to the lab with an authorization form, a drawing, the final design that has been approved by the supervisor, and telling the technician where to place all of the components. This secondary impression is poured using stone. The technician will then have the secondary cast ready. He is going to draw the final survey exactly as present in the authorization form. So the technician will do a blockout of the secondary cast. The blockout procedure will be described in further detail later, but the idea is to prepare the cast in a way that would follow the principles of metal framework design. So we need to do what we call a duplication. This is the secondary cast with the blockout material on it, and we need to place metal over it. So this material does not stand metal. Stone does not stand the temperature of the casting machine. So we need to use another material. We need to use another material that could stand the temperature of this process, and it's called refractory material. So how do I change this to this? I need a process called duplication. By duplication, what do? I simply take out the cast, put it inside this flask, and close it, and then pour over it a duplication material. This material is usually made of agar or silicon. Silicon is more accurate. Silicon comes in two containers as in a liquid form. The material from these containers are mixed according to the manufacturer instruction, and once they are mixed, they are poured inside the flask. Once it's set, we will get this where the cast is present, and we take it out, and we will have this mold, this empty mold. This empty mold now is ready to be used as a form for pouring in the refractory material. The refractory material is another material, powder and liquid, mixed together. Once we pour it inside here, we will get these refractory casts. The main property of the refractory material that it withstands high temperature, and it will compensate for the expansion and contraction of metal during the cooling process. Please review your dental material lectures and read your dental material chapters about refractory material. After finishing constructing the refractory cast, now they are ready for the step we call wax up. The wax up is done using wax patterns. These wax patterns come ready, and they are in the same shape that we want our final metal framework to have. As you can see, they come in colors, they have different shapes, but if I look at them, they have specific measurements that I need to incorporate in my metal framework. These wax patterns are then transformed into metal using the process of casting. It's a process that contains multiple steps, so let us take them one by one. This metal framework is then attached to what we call sprues. These sprues later on will be attached to a funnel. These are extra components essential for the casting process. This finished wax up with the spruing on and the funnel is placed in what we call an investment ring. Inside this investment ring, I am going to do another pour, but this time I'm going to use investment material. This is the powder, and it could have a special liquid to it or water, depending on the manufacturer instructions. These are mixed, and once we have the wet mix there ready, we pour it around the material. If I take this out and after it sets, take a cross section of it, if I open it, these are the layers inside. You could see the funnel that we placed at the last step of the wax up, the sprues, and the metal framework there, and we could also see the refractory cast inside. This is ready to do a step after it called burnout, because all of these spaces are filled with wax. We don't want them filled with wax. We want this wax to go out. So we do a process of burnout, where this is placed in an oven at high temperature. The oven will melt down all of the wax, And what we will have at the end, we will have this investment material with empty tunnels that follow exactly the same shape that we had in wax. These empty tunnels, this part is exactly resembling the funnel. These empty tunnels at the beginning are the exact duplication of the sprues, and later on inside you will have empty spaces where the metal framework wax up was done. Now this is ready to go to the casting machine. There is a place in the casting machine where this is placed and heated. In the casting machine it is placed, and another part of this casting machine we have the crucible. This will take the metal ingots in. These are the ingots of chrome cobalt material. They come in different shapes. This is one of these shapes. It is placed in this crucible and heated until it's molten. If you can look inside, as you see, this crucible has the metal still solid. Once heated to the temperature specific for chrome cobalt melting, it becomes liquid, and there a process of centrifugation, fast rotation, will take out this liquid from inside the crucible. You could follow the green color inside. It will go out this opening and go through a hot tunnel into the already heated investment ring. The metal will go follow the tunnel inside into the empty spaces, and it under force will go and flow into all of the empty spaces that were created by the funnel, the sprues, and the metal framework wax pattern. So after pouring the metal, it's taken out the casting machine and left to cool. And what I get now is metal inside this investment ring. So if I take the cross section of this, it will be this exact shape, but all of these are now replaced by metal. These are all in metal. After finishing the casting process, I began using a hammer to fracture off investment material. One of the properties of investment material that they have low impact force, so they can easily be broken. I break them down. I begin breaking off all of the layers. You can harvest now the metal with some investment material still around. This metal is further cleaned by hammering, and then you will get fine particles of investment. These are also cleaned by a process called sandblasting. And finally, I get the metal framework that was embedded inside this investment material, now free from all investment material. So see how the metal took the shape of the funnel, the sprues, and the metal framework that was made previously in wax. To finish this off, remember that these are not components that I'm going to place inside the patient's mouth, so we need to cut them off. We begin by cutting by specific discs. We begin cutting them. After cutting, we begin finishing them until they become totally smooth. And the metal is polished. This metal framework is now ready to go to the clinic. So the dentist receives this metal framework and puts it inside the patient's mouth and tries it in, then takes a bite. The bite registration tells us where to place the occlusal plane of teeth that we're going to select. I would like to remind you, with the bite registration you have done in complete denture, because in the case of free and saddle, this is very similar. So we do the wax blocks according to the instructions you have taken in your lab. We are going to do the same clinical steps that we're going to do in the clinic. But for the bounded saddle area, we simply place a block of wax and tell the patient to bite on it. This is called bite record. We also select the shade for the teeth we intend to use. So we do a shade selection. We write down the authorization form containing all of the information about the teeth that we would like to choose, their shape, their shade, their size, and this is all sent back to the lab, authorizing them to finish off the acrylic. In lab 3, we will have received these, and the technician will take these metal framework, for example, and using our record will begin placing teeth. Once the teeth are in there, now we call that a metal tri-end denture. It has the wax teeth and the acrylic. These are the acrylic teeth that will be in your denture later on. These are ready now to be sent back to the clinic. And the doctor has the denture there, partial denture there. He places it inside the patient's mouth. He tries it in. He makes sure the wax shape is suitable for the patient. He makes sure that all of the components of the RPD are engaging in their place. Make sure the occlusion is correct. The boundaries of your RPD are all correct. And sends them back with an authorization to do and complete the acryl. The wax is replaced into acryl using the same process you used in complete dentures, which is the flasking, then dewaxing, then packing, and finishing of acryl. After packing and curing the acryl, once we take it out of the flask, after deflasking, we will find that the acryl is rough. You will have some edges. These all should be finished. And the final acrylic RPD, after finishing and polishing, making sure all of its extensions blend smoothly inside and outside with the metal. These are sent back now to clinic number 5, where the dentist is ready to deliver this RPD. And I hope your patient goes out happily, and they might come in later on for a recall visit if they have any complaints to be treated on the spot, similar to complete denture procedure. Thank you.
the sprue arrangement, careful investment and preheating of the cobalt chrome muffles are crucial in ensuring the muffle is filled completely and the casting free from shrinkage cavities. The process technology involved is shown in this part of the cobalt chrome video series. To ensure the muffle is filled completely and the casting free from shrinkage cavities, all parts of the wax-up must be carefully applied or adapted with the rubber pin as shown here. This, however, is provided that the sprues are fixed in a manner appropriate to the casting technique, which is determined by the following general rule. The melt must be able to flow into the muffle cavity rapidly from thicker parts to thinner ones. Kinks, excessively long sprues or constrictions slow the flow, causing defects or porosity. This wax-up is to be cast with the Fornax high-frequency induction casting machine. The wax-up is carried out in such a way that no part of it can come off the model during fixing of the sprues and investment. Since they have a wide surface in contact with the wax-up, flat casting strips with a cross-section of 2 by 6.5 millimeters are very suitable for centrifugal casting. They are waxed onto the thickest points. This allows the melt to flow in rapidly and freely. And this largely rules out shrinkage cavities and porosity. Casting strips also act as reservoirs as the melt solidifies. 3 mm diameter sprues are sufficient for supplying the minor connectors and the clasps. The universal funnel former is carefully waxed to the sprues. Its low weight and the large diameter are advantageous. The sprues end in the middle of the model 10 mm above the highest point of the wax-up. The number of sprues to be fixed depends on the size and shape of the base. 2 sprues would normally suffice here, but the position of the bonwheel clasp and the thickness of the base necessitate an additional one with a diameter of 3 mm. This is the way it has to be done. This arrangement allows the melt to flow from thick to thinner parts of the casting object and contract without internal stresses and shrinkage cavities. If, as in this case, round sprues are used as an alternative to flat casting strips, they must be at least 3 mm in diameter. Aligning the sprues appropriately smooths the flow of the melt. Here, as well, the sprues are fixed to the thickest points of the wax-up. This skeletal base makes it particularly clear. To achieve a perfect casting result in this case as well, thick parts, like these backings in the anterior area, are provided with an additional 3 mm sprue. Round sprues, each with a diameter of 3.5 mm, are required for this sublingual bar. The sprue is waxed on immediately behind the finishing line in the retention area. This lower wax-up is cast through the model. If sprues with a diameter of only 3 mm are used, a reservoir is advantageous for the melt. This is a reliable way of avoiding shrinkage cavities at the sprue fixing points. The reservoir should be about 2 mm away from the wax-up. On this work as well, the sprues are kept as short as possible, but follow a slight curve to the casting object. All of the fixing points are waxed right around, without any gaps. This prevents any investment material particles being entrained with the melt as it flows in. With 2 sprues, the funnel former should be provided with additional stabilization. On this work for a patient's lower arch, the 3.5 mm sprues are led to the wax-up from above and waxed on behind the wax finishing line and onto the bar. They should follow a uniform curvature to meet in the middle of the model, 10 mm above the highest point of the wax-up. The shallow casting funnel former minimizes the height of the mold. Are generally sufficient in the lower arch. Additional sprues are only required for backings or other thick parts. For this wax-up, by contrast with centrifugal casting, vacuum pressure casting only requires 2 by 4.5 mm casting strips. Additional risers and pressure balancing channels are not required in the Bego system, since they have no significant effect on the casting result and metallurgical structure. Carefully tailored process technology and an efficient casting machine are much more crucial. Once the sprues and casting funnel have been fixed, the model is prepared for investment. This investment model is waxed onto the base plate of the mold former to prevent it coming loose as a result of the vibration. To obtain a smoother surface, the model is coated with the fine investment material Wiro paint before investment. The bottle must be shaken thoroughly before use to allow the fine investment to be applied at the right consistency. The fine investment is applied sparingly and evenly with a moistened brush. It reduces oxide formation to greatly speed up finishing. Investment is now carried out without delay to enable the still moist wiro paint fine investment to bond with the investment material. Otherwise, there's a danger of wiro paint that has already dried not bonding with the investment material. Models with an investment material base no longer have to be secured by waxing onto the base plate. To allow the investment material to flow more easily, the wax-up can alternatively be sprayed before investment with the wetting agent Oro film and then dried with low compressed air. This stops the wax repelling water. However, Oro film must not be used together with wiro paint. When the mold ring is put on, it must be ensured that it fits on the base of the investment model or the base plate without any gaps. This prevents rising air bubbles being trapped between the dry model and the moist investment material. Investment material and mixing liquid are to be stored at about 20 degrees Celsius. A climatic chamber is a suitable means of achieving this, but a fridge converted to the temperature range required can also be used. To achieve more stability for the muffle, 30% Bego Sol mixing liquid can be used, as well as distilled water. Before power mixing, powder and liquid must be mixed manually with a spatula for about 15 seconds until the material is uniformly moist. To avoid bubbles, the investment material is mixed for 60 seconds with a powerful mixer. The hose is not removed until the vacuum has been released. A handy hint to prevent bubbles at backings and parts that are similarly difficult to invest: investment is applied to the critical areas with a brush or an instrument before the mold former is put on. The investment is then poured in at a low vibration setting. It should flow into the mold in a thin stream from one side as seen here. The vibrator is switched off when the wax-up is covered. The mold former is removed after 10 minutes. The muffles are marked to enable the amount of metal required to be apportioned correctly. After 30 minutes, the investment is fully hardened and the muffle can be placed in the preheating furnace. The muffles may crack during preheating if the investment material is not allowed to set for the time specified. And now to recapitulate the most important points involved in fixing the sprues and investing the wax-up. melt must be able to flow into the muffle cavity rapidly. It is therefore necessary to avoid constrictions and sharp angles when fixing the sprues. Use casting strips that are as flat as possible in the upper arch. In the lower arch, 2 round sprues with a diameter of 3.5 millimeters are generally sufficient. Provide very thick parts with an additional sprue. And once again, to remind you, fix casting funnel former in the middle of the model 10 millimeters above the wax-up. The mold ring must fit on the base without any gaps. Wax in place if necessary. Mix the investment material manually for 15 seconds and then for 60 seconds under vacuum with a power mixer. Allow the investment material to set for the specified time. Before preheating, mark muffles to show later which wax-up is present. For preheating, the round side of the muffle must lie on the bottom of the furnace. Lay the muffles in a furnace which is cold or has been preheated to 250 degrees Celsius. The crucibles for high frequency and flame casting are preheated at the same time as the muffles. This extends the life of the crucibles and reduces the time needed to melt the alloy. The already installed Program 32 in the MIDI-Therm MP is used for cobalt chrome investment materials. User programs can be entered to supplement the 20 installed programs. "7:30 a.m. on Friday is chosen as the casting time. And the program is started. The thermal expansion curve of Wiro plus S shows an expansion of the investment material of 1.2% at 600 degrees Celsius, reached with a temperature gradient of 5 or 7 degrees Celsius per minute. This expansion of the investment compensates for the contraction of the alloys during cooling. The preheating furnace has now reached the final temperature. The end of the programmed holding time is indicated by visual and acoustic signals. Crucible and muffle can now be placed in the casting machine. Part 6 of the Bego Cobalt Chrome video provides detailed information about casting, finishing and polishing. A variety of casting techniques are used for melting and casting cobalt chrome alloys. This video shows the melting of cobalt chrome alloys with high-frequency induction currents and an open flame, and casting using the centrifugal and vacuum pressure techniques. The crucible preheated with the muffles has been placed in the centrifuge for casting in the Fornax 35K. the ingots lie close together for even preheating. A measuring cell registers the infrared radiation emitted by the melting alloy and converts it into an electrical pulse. This pulse controls the induction current to prevent the alloy being overheated during melting. Interrupted preheating, which is also called cycling, allows even melting of the alloy. The muffle, preheated to 1050 degrees Celsius, is now inserted. Melting of the alloy now proceeds rapidly. In the case of wyronium extra hard, centrifuging is started with the lowering of the crucible coil 2 seconds after the shadow disappears from the melt. The centrifuging time is set in the factory. Melting with a flame is an alternative. A mixture of acetylene and oxygen, propane and oxygen, or the natural gas and oxygen used here is suitable. The Fundor T motorized centrifugal casting machine has a continuously adjustable starting speed to enable it to cast different alloys better. The double-jointed arm ensures a high centrifugal force. The counterweight can be adjusted for the mold size without problems. Tinted goggles must always be worn when melting with a flame. The automatic gas igniter helps considerably. When the burner is replaced in the holder after melting, its flame is extinguished without altering the setting. When the casting sequence is rapid, the burner can be reignited with the pilot flame. The burner is guided over the ingots about 6 to 8 centimeters away. This is the only way of heating the alloy, wironite in this case, evenly from the outside to the inside. The moment for casting is reached when the liquid melt moves through the pressure of the flame. For safety reasons, the cover of the machine cannot be opened until the centrifugal arm has come to a standstill. Ongoing development of the casting technique led to the microprocessor-controlled high-frequency vacuum pressure casting machine in the form of the Nautilus MP. The casting program for a specific alloy, wironite extra hard, is being loaded here. Preheating is used with this casting technique as well in order to heat all of the ingots evenly. The preheated muffle is placed in the lower chamber. Once melting has started, the chamber is evacuated and the alloy melted under vacuum. During melting, a microprocessor acting as the central control unit constantly calculates the change with time in the infrared radiation emitted by the alloy. The digital display shows the current information about the casting sequence. The infrared value being measured drops when the skin of oxide cracks. This change is detected by the sensor and the right moment for casting calculated by the microprocessor. The signal indicating readiness for casting is given, and casting started as soon as the casting temperature is reached. The crucible opens and the melt flows into the muffle. Only then is the vacuum released and the melt forced into the muffle under a positive pressure. This ensures it reaches even the most minute cavities in the muffle quickly, yet in a controlled manner. Whatever the casting technique, the muffles must be cooled slowly to room temperature after casting. This avoids inducing stresses in the metal as a result of cooling too quickly. Only muffles that have cooled down completely can be immersed in water to avoid dust during deflasking. The casting is now released carefully from the muffle. A small deflasking chisel or a hammer applied to the casting cone is a suitable tool. The investment is removed in this way without damaging the casting. To make blasting easier and quicker, as little investment as possible should adhere to the casting. The investment and the oxide layer are now removed with pure aluminium oxide in the form of Corox 110, in this case, at a maximum pressure of 4 bar. Critical areas, such as the insides of clasps and stabilizers, are blasted with Corox 50 at reduced pressure. Chrome frames can be blasted manually or automatically with the Aqua Mart wet blaster. The wet blasting technique gives a silk finish and lower surface roughness than blasting with dry corundum. The important thing is that absolutely no dust can be generated. Here, where accuracy is what matters, directed blasting is carried out with the fine jet pencil, first with 50 micron aluminium oxide and then with 50 micron perlablast. The sprues are separated safely and faster on the high-speed grinder with built-in extraction system. Here, small separating discs with a diameter of 25 mm and a thickness of 0.5 mm are used. Once the chuck has been released, the tool can be changed quickly without having to switch the motor off. The fixing points of the sprues are ground with a perforated disc. Finishing can be completed with the high-speed grinder or the handpiece. Sintered diamond grinding stones have proven very effective for finishing cobalt chrome alloys with the handpiece. Diamond grinding stones are much more cost-effective than ceramically bound stones. In the interest of safety, the maximum speed of 30,000 revolutions per minute must not be exceeded. The dorsal finishing line is smoothed with a fine-grain grinding stone or, as in this case, with a sintered diamond one. When using sintered diamonds with a diameter of more than 5 millimeters, the speed is reduced to 10,000 revolutions per minute. The finishing lines must be demarcated carefully. The tips of the clasps and the rests should be rounded slightly. Critical areas between clasp elements can be separated with a small separating disc or a sintered diamond point. Clear demarcations must be created with the sintered diamond point in order to achieve a transition without gaps between the metal base and the acrylic saddle to be fitted later. To avoid impairing their shape and stability, small, very carefully modelled supports should only be finished with the rubber polisher. When stippled surfaces, such as this base, are finished with a blunt carbide rose drill, electrolytic polishing is more effective. Blasting with fine aluminium oxide and perla blast before polishing improves the surface finish on the insides of the clasps and rests and enhances the final polish. The object is secured with an alligator clip and attached to the moving anode. An additional cathode can be attached to polish the stippled palatal area adequately as well. The tip of the curved copper rod is fixed at the lowest point of the upper base without coming into contact with it. Firm and secure contact is important for a good result. The cobalt chrome frame must not be in contact with the negative pole, that is the cathode. Otherwise an overcurrent will flow, causing the unit to switch off. Bago will take used Wire-Lite polishing liquid back on payment of a charge for disposal. The Ultrapole SL has 3 current settings. Polishing for 4 minutes with a current of 6 amps and a bath temperature of 40 to 60 degrees Celsius gives a good result. Further polishing is not required. Electrolytic polishing removes roughness in the form of minute edges and tips. Excessive polishing jeopardizes the fit and dimensional accuracy of the clasps by removing too much material. It is advisable to work with a masking lacquer such as Seculac on critical areas such as stabilizers, female part holders, delicate clasps and rests. It's applied sparingly, dries rapidly, and is easily peeled off after polishing. No material is removed from the masked areas. After polishing, the cobalt chrome frame is rinsed and thoroughly cleaned with the steam cleaner. The frame is now placed on the model. Sprinkling talcum powder on the plaster teeth allows the polished frame to slide onto the model easily. Here a duplicated working model made of Bago stone is being used to avoid damaging the master model. This enables the dentist to better evaluate the design and effectiveness of the prosthesis on the undamaged master model. The frame is now removed from the model and reworked here, where there is still slight interference, using a fine-grained sintered diamond or rubber polisher. Only the bottom edge of the clasp is rounded with the rubber polishing roller. The accuracy of fit, and hence the retaining effect of the clasp, is reduced every time material is removed. Base, sublingual bar and minor connectors are smoothed with a small rubber polishing wheel or rubber roller. Outside surfaces of clasps and rests are rubber polished with a green soft rubber polishing point. Separated or relatively inaccessible areas are rounded with a knife-edge wheel or small wheel. The basal surface of upper frames is only rubber polished in exposed or concave areas. A surface with a lasting high polish can be achieved with a medium hard polishing brush and small amount of cobalt chrome polishing paste. Areas that are difficult of access can be polished with a small stiff brush with a metal hub. To avoid scoring, the direction in which this polishing is carried out must be constantly changed and the frame supported securely. The handpiece brush can be used with cobalt chrome and diamond polishing paste, as shown here, to improve polishing of metal masticatory surfaces or backings. Finally, the frame is high polished with soft linen. The surface consolidated in this way prevents plaque building up. The cobalt chrome frame, which has now been polished, is cleaned thoroughly with the Triton steam cleaner. The frame is now placed on the master model and checked for accuracy of fit. The tip of the clasp chafes at this point when the frame is placed on the plaster model. The clasp bends up here at the natural tooth and slides over the greatest diameter into the retention area. Since clasp protheses are not secured on the remaining dentition as firmly as attachment or telescopic work, clasp arms, rests and the base must fit accurately without inducing stresses. It is evident on the master model that the dental design of the prosthesis meets the requirements for maximizing the exposure of the periodontium. This upper and lower archwork for patients, which has already been shown in the preceding parts of the video, can now be inserted by the dentist as a frame at first, and then with wax rims for registering the bite. The minimum gap of 4 millimeters required between base and marginal gingiva has been achieved. The dentist checks the fit of the frames and the bite situation in the patient's mouth. The shape and size of the rests and clasps are planned out to avoid impairing the articulation. The physical properties of the Bago cobalt chrome alloys allow slender clasps. They are characterized by particularly high ductile yield in conjunction with high strength. Even in the case of combined work, as with the Ancora Rod Attachment here, a functional tooth replacement that fits accurately is no problem using the Bago system. The rigid connection between the saddle of the prosthesis plus the base and the remaining dentition is provided here by a sublingual bar made of Wiron-It extra hard. On the primary frame made of Wiron 99, milled shoulders and an interlock hole are provided to guide and support the prosthesis. The Ancora Rod Attachment is a rigid extracoronal profile rod attachment for partial prostheses. The replaceable female parts are elastic and extremely tough. The interlock hole opening in the basal direction has proven very effective from the point of view of hygiene. The stabilizer is shaped anatomically. The pontic-like shape of the first replacement tooth exposes the periodontium. The cavity for the female part holder has been blasted with fine aluminium oxide and masked with Seculac for electrolytic polishing. This is important in ensuring the female part holder seats accurately. It is pushed into the holder with the impression pin. It's also possible to leave insertion of the female part until the cobalt chrome work with teeth and acrylic is completed. Thus, it is possible, with carefully tailored process technology and appropriate materials and equipment, to achieve reliably reproducible results. The work is finished in the dental lab and then inserted by the dentist.